Hello everybody, welcome to this Houdini tutorial. We're gonna take a look at how to create a Houdini FLIP Fluid simulation of two differently colored liquids that are crashing into each other. We want their colors to mix, and we want to be able to export this mesh into Maya and Cinema 4D while keeping the colors intact. We also want to export arbitrary attributes on the mesh to another host application as well. So at the end of the video, I will cover the Alembic export and the creation of custom attributes on a mesh. So yeah, let's get started. The first thing that we actually will need is the actual FLIP Fluid simulation. And yeah, to create a simple liquid simulation, we're just gonna create a sphere. So we're gonna dive into the sphere's network to change its primitive type to polygon mesh. And with the sphere selected, I'm gonna go up here to our particle fluids shelf, which I've already selected. And here I'm gonna create a I'm gonna emit particles from our sphere using the emit particle fluid shelf tool, which will create the needed node networks for us. So clicking it, it actually wants me to pick a fluid to emit into, but there is no fluid yet in the scene. So I'm gonna press enter anyway, and Houdini will create the required node networks for us. So taking a look at the node networks, we're not gonna use or need the particle fluid interior for this tutorial, and instead we're gonna concentrate on the sphere, the autodop network, and the particle fluid, which are the most important nodes for our simulation. And right now I'm just gonna jump into the sphere node because a couple of things have changed here. As you can see, Houdini added a few nodes that we need for a flip simulation. And as you can see, our original sphere is fed into a create surface volume node, which creates a volume representation of the sphere, which is used to emit particles into our flip simulation, and everything at the end is fed into this null object, which I accidentally disconnected here, which happens all the time and I hate it. And yeah, this is just a null, and basically it's the end of these operations that are being done to our sphere geometry. Something that Houdini also created is our autodop network, which yeah, basically is the environment where all our simulations are taking place. And if we jump into this real quick, we can see that Houdini unfortunately completely messed up our node layout, which happens from time to time, which I also hate when it happens. But anyway, we can just rearrange our nodes to our liking to make it a bit more visually pleasing. And after having arranged everything, we're just gonna take a look at what each of these nodes is actually doing. So as we can see, we've got a source surface from sphere node, and this node is actually used to bring in our volume representation of the sphere from outside the autodop network, as the sphere is within this sphere geometry network. So as you can see, there's no connection between the sphere and the autodop network, and that is because the source node is used to bring the geometry or the volume representation in. So you can see there's a path on the node that is pointing towards the out surface node, which is the end output of all the operations that are being done to a primitive sphere to create a volume out of it. So what the source node does, it just brings in this volume into the autodop network, which is our simulation environment. And it is fed into this merge node, which would be used to hook up additional sourced volumes together to feed them into the flip solver, which is doing our actual simulation. And it basically outputs the finished simulation as particles, which is used elsewhere in Houdini. So there are a few other nodes, which is the flip fluid object, which is basically our flip simulation geometry, and there's also another node which is the gravity, which is forces that you can apply to our simulation. We're gonna leave the gravity unchanged because we actually want to have gravity in our simulation. And the third and today most important node is the particle fluid node, which is the actual generated fluid. So if we run through the simulation for a few frames, we can see how the particles, the flip particles, are emitted from our sphere geometry. And if we dive into the particle fluid, we can see that it is also bringing in geometry or a simulation. So what it does is pointing to the flip fluid object within the Autodrop network to bring it in, and what it brings in are points, which you can also see in the viewport right now. And there's also this particular fluid surface, one node, which we're going to take a look at now. I'm just going to move it off to the side here to make it a bit more visible. And this node is actually used to mesh the particles. So if I set its display flag, you can see that it actually outputs a surface based on the flip particles into our scene. And there are a few other nodes here, like the fluid compressed node and the compressed cache, which are all the nodes responsible for caching out the fluid. You can cache out just the particles without the finished meshed surface, and you can also, of course, cache out the calculated surface of our fluid simulation. So this is just a quick overview of the nodes associated with the simulation. I'm gonna rewind it here. So as we can see, our particles and the resulting mesh based on the particles is being emitted correctly. However, I do want to change a few things about the simulation, and the first thing I want to change is our particles being emitted sidewards, so they can crash with other particles emitted from roughly a position here. So let's do that right now. We've got to change a few properties on our emitter. So we're gonna go into this create surface volume node, which has a velocity volumes tab within its parameters. So we want to add a little bit of velocity to our flip particles that are being emitted, and we do that by checking this little add velocity checkbox, and I want to give them a little initial velocity along the z-axis, and we can actually see a little representation of the direction of the force that is being applied. And changing that to 4, we can see that is gonna direct our particles along the z-axis in a positive direction. So if we rewind our simulation and have it play, we can actually see that our particles are being emitted with a certain speed sidewards. So the first thing that we notice about our fluid surface is that it's actually colored bluish, and we don't want that, or maybe we want that, but I don't want that right now. So I wanted to have a prominent color, something like yellow or similar. So the way we do that is that we use a attribute in Houdini which is called CD, which is short for color diffuse. And to do that, we have to change a few things within our emitting geometry. So this CD attribute is stored on points in Houdini, and it is actually being read by the viewport. So if any mesh has a CD attribute associated with its points, the viewport is gonna display it in that color, and the renderer mantra is actually also gonna use that color. And to do that, there are actually 2 ways, and we're gonna go the easy way right now, which is to just use the color node, which sets the CD attribute on our mesh. And what we want to do is we color the emitter. so that the particles inherit its color. So we're gonna use this color node, which I've already added, and we're gonna change its color to something yellowish here. And as you can see, its volume representation changed to a yellow color. So what we want to make sure now is that our particles are actually inheriting the color of the yellow sphere. So we're gonna dive down into our particle fluid, and we're gonna set the display flag to the import particles. And as you can see, they're currently white because they've already been emitted. But if we rewind the scene again and let it play, we can see that our emitted particles are actually colored yellow, which of course is what we want. But what we don't have right now is our fluid surface actually being colored by the CD attribute. So our particles are actually yellow, and as you can see, our surface is still unfortunately blue. So we have to make sure that our surface gets colored by our particles, and we can quickly check the attributes on our particles within the geometry spreadsheet, which as you can see lists all the points within the import particle node. So there's a XYZ coordinate for P, which is the location of the points, and you can also see this has the CDR, CDG and CDB attribute, which is set to a yellow color, which is 10100. And yeah, this is just a quick way to check that your geometry actually has the attributes that you want it to have. So why doesn't it show up on our surface? Well, the reason for this is that we did not actually tell our particle fluid surface node to inherit the CD attribute, and it's not being passed on to the surface measure actually. As you can see on this fluid compress node, which is used in the caching of the fluid, it stores a lot of attributes within the cache, which is vorticity or V, the velocity, but not CD. So we're going to add CD and press enter to actually store the CD attribute as well. But as you can see, our surface is still not colored yellow. And this is because we haven't yet told the surface measure to pass on the CD color attribute to the resulting surface. And we do this in this little tab that is called transfer attributes, and we're gonna add CD so that the CD attribute is transferred from the imported particles to the resulting shape that we're outputting. And as you can see, as soon as I click enter, our liquid surface is colored yellow. So having done that, I'm just gonna fast forward a little bit here through the video. You can see that the liquid is emitting from the sphere and it is colored yellow. But what we wanted to have is a second fluid which crashes into the first, and this fluid is supposed to be differently colored, so that we had a little bit of mixing here. And to do that, we're going to create a second sphere, and we're going to use it as a emitter, and we're going to move it off to the side. So to create a emitter from our second sphere, there are basically two options. We could use the shelf tool again, but instead of doing that, I'm going the kind of manual way of constructing the network to emit a second stream of liquid. So what we're going to do now is we're going to select all of these nodes that are responsible for creating the volume representation of our first sphere, and we're just going to copy them, and we're going to paste that into our second sphere. And as you can see, it actually correctly created volume representation of our second sphere, which is colored yellow, and it has exactly the same parameters as our first sphere. So obviously the first thing that we want to change about this is the color. So I'm gonna pick something bluish greenish here, and as you can see, the volume representation picked up the color. If we rewind the scene now, you will see that no particles are being emitted from our second sphere, and this is because we haven't brought it into our autodop network yet. What we have to do to make it become part of our simulation is we have to bring in its surface, or better said, its volume representation into our simulation environment. And I'm just going to copy and paste our source surface from CO1 node, and it's actually pointing to the first sphere, and we want to change that. We could change the path manually up here, which sometimes is faster, but there is also a little pop-up menu that you can use to have it point to a different operator within your scene. And for this we're going to choose the out surface node, which is the end null in our sphere 1 node. And obviously this changed the path. What it did not do is make it part of the simulation. We're going to do that by merging the two geometries together. And as you can see, our blue sphere is now producing flip particles. So we're going to rewind this here and play it again. And as you can see, our blue sphere is emitting particles basically in the same direction as our first sphere, and colored blue. Now what we want to change is we want the fluids to crash, so I'm going to change the added velocity on our second blue sphere to -6 along the z-axis. And if we now play the simulation, we can see that two differently colored liquids are being emitted. So I want to change a few things here. The first thing I want to change is I want to move the spheres closer together, so the liquids are kind of crashing earlier, because I really don't want to cash out a lot of sim frames here to get to the point of this tutorial, which of course was coloring the exported Alembic mesh. But as you can see, our liquid surfaces are colliding, and we already get a little bit of mixing of the fluid colors right there in the middle. And as you can see, there's little spots of blue and yellow everywhere, which obviously is what we wanted. So what it does is it picks up the CD color attribute from the individual points of the particle simulation, and it colors the surface accordingly. What we do not get from that is basically a complete mixing of the fluid colors. You can see it's kind of spotty, which a lot of liquid simulations do. The realistic way would be to well, kind of create a third color from the two colors, which would probably be a dark green in this case. You can actually do that, which requires a more complicated node network. But I guess this is enough of mixing for this short tutorial. So let's kind of start thinking about the export here. So we have a meshed liquid, and we're ready to export it out as an Alembic file. And so let's just do that right now quickly. So I'm going to hook it up to our particle fluid surface node, and I'm gonna pick a path. So I'm gonna pick our current job directory, and I've already got a folder there for testing purposes. So I'm gonna create a second one, and I'm just gonna call the Alembic file fluid out surface colorless .abc. So to export our geometry, we're gonna go up into the file node, and we're gonna change it to right. So it is now written out our Alembic file, our Alembic geometry, and if we switch to Maya here real quick, we can import the Alembic file. So let me just quickly navigate to the correct folder here, which is Houdini Asset Tutorial 2, and I'm gonna select the output Alembic file, and as you can see, there's our liquid mesh. Looks exactly the same like it did in Houdini, which is great. But as you can see in the color sets tab here, there are no vertex colors associated with this. So obviously we didn't bring in any colors and we can't show them within Maya. So obviously this is not what we want. We want to get all those attributes transferred over from Houdini to Maya. So going back to Houdini, we'll have to change a few things to actually make this work. So what we have to change is, as I said before, CD is a point attribute, and what we can write out as variables into an Alembic file are vertex attributes. There is a small but important difference between points and vertices, so we have to convert our point data to vertex data, and we do that by using a node called attribute promote, which I'm searching currently and can't find, still can't find. There it is. We're just gonna hook that into our node tree, and having done that, you can see there are a few options in there, and we have to supply the name of the attribute that we want to promote or change, which is CD in this case, and its original class is point and its new class is vertex. So having done that, we are basically ready to write out a new Alembic file, and I'm just going to delete the file node here and recreate it, because I've made the experience that Houdini sometimes likes to crash when doing too much while having a file node hooked up to the tree. So I'm gonna just save it here and call it tutorial, not tutorial, which obviously is wrong. So .hip. So now that we've saved our scene, I'm gonna save out our Alembic cache, and I'm gonna call it color basic, because right now it should store our color per vertex information, our CD attribute, if we have done everything correctly, which I think we did. So I'm gonna change it to right, and going back to Maya, I'm gonna delete the old imported Alembic file, and I'm gonna go to Alembic caching, import Alembic, choose the color basic one, which we just exported, and as you can see, voila, there are colors on our match, which is great. So let me just change this to diffuse here to make it a bit more visually appealing, and as you can see, it looks exactly the same as in Houdini, and yeah, that's the way we can bring in the CD attribute into Maya. So in a lot of cases this might be enough, but usually you want to export a bit more of information for shading purposes or other purposes to your host application if you're shading outside of Houdini. And one thing that you're often going to use is the velocity to color parts of your liquid differently if it's traveling faster or slower. And the particle fluid surface node has a visualizer associated with it that you can use to visualize the velocity on the surface very quickly. As you can see, this is basically a ramp going from dark blue to turquoise to white. And you can see fast moving parts are well, colored lighter, while slow moving parts like the top surface here are basically not moving at all or much. So obviously this is all quite nice, but you have to keep in mind this visualizer is a visualizer. So if we want to store this information on the mesh and not just visualize it in a Houdini viewport, there are a few different options to actually do that. And the way it's usually done is you create a new custom attribute on your mesh surface to store exactly the information that you want in a format that you want, because you may not want to store the V attribute, which is velocity, directly, but manipulate it So the first thing we're gonna do is we're gonna go to a attribute create and create it. The attribute create, yeah, always creating something. So we're gonna call our new attribute custom velocity. And we want to check a few things here to make sure that it is of the correct type for our purposes. And in this case, it's going to be a point attribute because it has to be stored on every single point on the surface. And we're going to make sure it's float, which is good for our purposes. It's 32-bit. We're going to change its size to 3. Because we need 3 channels for the colors red, green and blue, obviously. So having done that, we're gonna change this to color because we want our channels to be called .r, .g, .b and not XYZ, which is important for the Alembic export. And the next thing I want to make sure is that we turn off our visualizer on the surface here so that we can see our surface unchanged. And we're gonna go to our geometry spreadsheet, and as we can see, our custom velocity attribute actually shows up, which is good because it seems to work. The attribute has been created, but we can see that it actually doesn't have any values. Right now they're all 0. So the first thing for testing purposes that we want to make sure is that we get the right values everywhere, and we're going to create a visualize node for that, which is basically used to visualize any arbitrary attribute, point attribute on the surface. So right now it doesn't display anything, which is because we haven't set an attribute yet. So if we change it to display CD, the visualizer will show us the CD attribute on the surface. So right now it looks like the mesh that we have before, and if we change that to custom velocity, we can actually see that the mesh is displayed black, and that is because our surface attribute called custom velocity right now sits at 0, 0, 0. And if we change our attribute, for example, its red value to 1, the visualizer will show us a red surface, which obviously is correct. I'm just gonna turn off showing the wireframe here so that you can see the mesh without the wire overlay, which looks a bit nicer. So if we now change our attribute to 101, which is obviously green, we can see that our mesh displays green, which shows us that our attribute is working correctly. We can check this again in the geometry spreadsheet, and as we can see, all of our points have an associated custom velocity attribute, which shows us 0, 1, 0 for each individual point, which is great. So one thing you maybe saw in the geometry spreadsheet, which I've mentioned before, but I'm going to mention it again, each point also has by default an attribute called V in Houdini, which is velocity. So this attribute actually stores the velocity information on the points, for example, for use in motion blur calculations. And if we just want to store that V attribute in the color for our mesh, there's actually a simple way, which I'm going to show you. You can use the attribute swap node. And what this does, it swaps 2 attributes. If I type in CD and V and set its display flag, you can see that our CD attribute is now taking over the value from the V attribute. So what you're currently seeing is the velocity, which is a vector attribute, obviously, copied over to the CD attribute of our mesh. So, however, this is not really what we want, so I'm gonna delete the attribute swap. What we want to have is more or less a color gradient representing the magnitude of the mesh velocity, to use it in shading. To, for example, give the fast moving parts of the liquid a slightly brighter color than the dark, slow moving parts. So what we want in the end is maybe something that looks more like what this visualizer node shows us if we actually activate it, and that we have a ramp that goes from bright to dark for the velocity magnitude. And the way that we're gonna do that is we're gonna use something that's called an attribute VOP. And VOP is a different class of nodes in Houdini, which are VEX operators. VEX is actually a language, a programming language, a script language, if you want, within Houdini that you can use to code very efficient functions within the program. And VOPs are kind of a visual representation of this VEX code. You can think of every single one of these nodes as a collection of source code snippets that get evaluated very fast. And if you're familiar with other 3D applications, for example with Cinema 4D, it has something called Expresso. And Expresso basically is a visual node-based system that lets you connect different functions, for example math functions, together to create a network that gets executed and manipulates data. So what we're gonna do now is we're gonna do just that with our V velocity data, to kind of give it a look similar to what we see in the visualizer, and we're gonna store this custom velocity in the variable that we called custom velocity. So you can see there are two nodes already in the attribute VOP. They're kind of like the input and output, and as you can see on the output, there are a few attributes available there, which are P, V, and also CD. But what we do not see is our custom attribute that we created. And what we have to do to export data from within the VOP to this custom attribute, we have to bind it. So what we're gonna do, we're gonna create a bind export node, and we have to name it the same name as the variable that we created on the mesh. So in this case, we're gonna call it custom velocity, which is what we called our attribute. So custom velocity. And having done that, we have to change its type. Well, let me first hook up the input just to V to see what's happening, and we can see that we get the V representation in our custom attribute. We should change the bind export type to 3 floats vector, which is the same as the attribute custom velocity that we created. So this exactly would be great if we want to export the velocity as Vertex Colors. If we need to pick them up in our renderer to tell it in which direction to motion blur parts of the surface. So it's actually quite useful to export exactly what we built here. However, what we want to create is a custom representation of the velocity, and essentially what we want to take is the length of the vector, which is kind of the speed or the magnitude, and there's a node that is conveniently called length, which gives us the length of the velocity vector, and we're gonna hook it up to V. And what we want to do now is we kind of want to well, not directly output the length of the vector, but we want to kind of colorize it by ramp. So within the attribute VOP, we're now gonna type ramp, which gives us this ramp parameter, which is unfortunately hooked up by default. We don't want that. We want to drive this ramp by the length of the V vector, and what it did is, if we go to the top level of the attribute VOP, we can see that it now has a new parameter interface, which is a ramp, which right now goes to black, from black to white. And what we've essentially done is that our vector lamp is driving this ramp, and we can manipulate this ramp at the top level without having to dive down into the attribute VOP every time we want to change a parameter. And if I deselect the geometry now, you can see that it's actually well, a pretty uniform color, and that is because we did not remap the vector length to a range that the ramp can use, because the ramp's range is 0 to 1. So we're going to use a fit range node to kind of push down the values into a range that is suitable for the ramp. So if we change that to 0 to 10, which will remap 0 to 20 to 0 to 1 for the ramp, we can actually see that a bit of black starts to show up at the top where the surface is not moving very much, which is exactly what we did within the ramp parameter. So now if we change parts of the ramp, you can see that our representation of the attribute updates. And if we kind of basically invert the ramp, you can see that all the parts of the surface that are not moving are displayed as more or less bright, and the parts that are moving are black, but we usually want it the other way around. So let me just fix the ramp here again. I'm going to set it to black. And yeah, as you can see, this gives us a nice representation of our vector. Now, if we want, we can probably change this maximum value to something like 20 or maybe 30. And if we adjust the ramp accordingly, you can see that we get more of a finer resolution of values, or gradation of values, which is probably what we would want in this case. And as you can see, on the attribute spreadsheet, our custom velocity is fed with the results of the attribute VOP that we created, and basically each point has a very different value right now. So we're now basically finished within Houdini. The one thing that we have to change is, because our custom velocity attribute is still a point attribute, which does not get written out to the Alembic file in a way that can be read, we have to promote it to a vertex attribute again, and we can use the same attribute promote node that we have before. So I'm just gonna type in custom velocity, and we're ready to go export our Alembic file. So we're gonna create a file node again and hook it up to our network, set its display flag, and we're gonna write it out as, well, we call the first one basic, so we're gonna call it advanced, maybe, because it's a super advanced color setup. Well, probably it's not, actually not, but brights out a little bit more than the one we had before. So having changed the right flag, it's actually exported our geometry, and I'm gonna switch back to Maya, delete our previous export, and go to Alembic caching and import Alembic and load our advanced fluid simulation. And as you can see, it brought in the mesh with the custom velocity as our primary color right now. This is because, well, it kind of reads the attributes from the Alembic file in reverse order. So everything looks the same as it did in Houdini, and we can see we also have our CD color set associated with the mesh, which it brought in from the Alembic, and switching to that, we can see it looks exactly the same as in Houdini. I'm gonna switch to diffuse because it looks a bit lighter. I should have selected the mesh, of course. And yeah, that's it. So now switching to Cinema 4D, we're gonna merge in our exported Alembic cache. We're gonna go to this asset tutorial, fluid out surface color advanced, and you have to make sure to check this little checkbox, or Haken as we like to call it, which is called color maps, which lets the Alembic importer read the color maps. And as you can see, we've got a small liquid mesh, pretty small actually, and there are two tags associated with it, and they are storing our color per vertex information. As you can see, anything looks exactly like it did in Houdini. Well, as I said before, one thing that is not happening right now is a actual mixing of the fluid. Well, you can see that the colors are blending together in this kind of outer region, but essentially it is picking up the color of the particles, and it is kind of interpolating between the particle colors. But what will happen in reality is that you would probably get more of a greenish colored liquid where the blue and the yellow fluid mix, especially if they kind of have the same density. So we can do that in Houdini with subsolvers and certain different techniques using VOPs again. I thought it would be too much for this quick overview tutorial to actually do today. If you have questions how to do it, feel free to ask. I might cover that at a later step, but you probably will also find resources for that on the internet. So I wish you all a great learning experience with Houdini, or if you're not new to Houdini, maybe you've learned something new as well. Wish you all a great day, and yeah, keep on experimenting. Bye.